Hello, Chem AP lovers. Time to shut down TikTok, Xbox, or whatever stuff you've been doing and get serious. Okay? So today, Mr. Moore and I are trying to take you through electrolysis. Now, electrolysis is the opposite of a battery, okay, which can be confusing. So remember, there's a few basics here. An amp is a measure of coulombs per second. Volt is a measure of joules per coulomb. And hopefully you remember deriving Faraday's constant, 96,485 coulombs per mole of electron. We're going to need to use some of those. Now, because electrolysis is based on a non-spontaneous redox reaction, you have to have a power supply or a battery to force this process to happen. Okay? And so the electrons don't want to move, and you have to make them move. And so a power supply has a negative and positive post. Okay? The positive post is now the anode. This is reversed from a battery. Okay? The power supply literally is ripping electrons away from the anode because it doesn't want to lose those electrons. The cathode is still reduction, and the power supply is forcing those electrons to go in, where in a battery those electrons voluntarily went in. So remember, the anode is always oxidation, cathode is always reduction. It doesn't matter what type of cell it is, but if it's an electrolytic cell, you need a power supply to force those electrons to move. I think Mr. Moore has a setup back here to give you an idea of what it might look like.
This is what we're looking out at today. Looking forward to having all of you back in those seats.
Indeed. It's kind of quiet here.
It is quiet.
Okay, so here we have a power supply with positive and negative post.
They're even labeled. You
Yep.
can see that. They're always, black is always negative, red's always positive.
And what we've done is we've wired it to an ammeter. This will measure the current flow.
Got that A on it.
Yep,
Tell
A
you what
for
it is.
amps.
Yep.
Okay, and then finally we are running our electrical current through the actual cell, right? It has electrodes in it, and then back to the power supply. Okay, so this being the positive post, okay, here is your anode, here's where oxidation is going to be happening, and here's the negative post, and this is where reduction will be happening at the cathode. Now, we don't have anything in the beaker, but you could imagine using this setup to pass electricity through some sort of cell and forcing those electrons to move. Okay, so when it comes to electrolytic cells, there's two types, okay? And the key is that the ions have to be free to move. If the ions can't move, then you cannot electrolyze something. There's two ways to make that happen. You can melt the ionic compound, melt the salt, make it molten, then the ions can flow. Or, if it's something that'll dissolve in water, you'll have an aqueous solution, and you can electrolyze either of those. And we're going to start here today talking about molten salts because they're a little easier to deal with. And I always like to start easy. Okay, let's see if we can get the screen on. We'll try to show you a couple of examples here. See if it makes sense. So here's one potential question. Could you find the mass of product formed at each electrode if molten aluminum oxide is electrolyzed with 5 amps of current for 5 hours? And really what this boils down to is trying to figure out how many moles of electrons are you pushing through the cell. And so we're going to calculate that using the amps and the hours. So remember that an amp is coulombs per second. It has time in it, but we'll have to convert to seconds if it's not in seconds current. All right, right, so can you convert 5 hours into seconds? How many seconds are in an hour?
60 times 60, I think.
I think you're right, Mr. Moore. So we got 5 hours, 1 hour, 3,600 seconds. So we cancel the hours. If you love factor label problem solving, this will be fun. Okay, now we're going to cancel the seconds out using the amps. Remember, it's coulombs per second.
Yeah, amp is a measure of current. So we got volts measuring the potential difference, the voltage of a cell. The amp, though, we need the amp. That we get that from the power from the wall. That power supply determines how many amps.
Okay, so we've multiplied by our coulombs per second.
Yeah, that was the problem said 5 amps of current.
Right, there's our amps. Okay, now we can use Faraday's constant. It has coulombs in it, and we're going to use that to help us figure out how many moles of electrons we pumped into our cell. But of course, we're going to have to flip it over because we have to get the coulombs to cancel. So there's 96,485 coulombs for every 1 mole of electrons. Okay, so we've canceled that out. If they give you amps and time, you're always going to start the problem in this manner. Always going to look the same. Okay, now we just have to think about what's going on at our electrodes. Okay, so if we're electrolyzing molten aluminum oxide, I've got aluminum ions that are going to have to gain 3 electrons in order to reduce to aluminum metal. The metal will always be reduced, and the oxygen is going to have to oxidize. So we'll have oxygen ions, because it's aluminum oxide, right? And they're going to have to lose electrons. Did I do this right, Mr. Moore?
Well, I guess we're going to make O2, yeah, so we need to change our coefficients, don't we?
We take 2 electrons, but it's,
Well, yeah.
it's 2 here, though.
Right.
Right, and so then I think we'll need 4 electrons
Yep.
altogether. Okay, we need our half reactions because we need these mole ratios here. Okay, so now I'm going to start this way, and that would give me some number of moles of electrons. Okay, and so whatever that number is, I can carry it down here. And if I want to know the aluminum, for instance, I can say that for every 1 mole of aluminum, it requires 3 moles of electrons. And if I want to know grams, that's an easy conversion. Okay.
Okay, that'll get us the number of grams of aluminum.
Right? Or if you wanted to know the oxygen, it would be the same thing, your moles of electrons, but now it'd have a different mole ratio, because
Yeah,
I would
from
say
up
for
there.
every 1 mole of oxygen, there's 4 moles of electrons.
Yep.
And then I would multiply by the molar mass of oxygen. And I would have my answer. Did I leave anything out, Mr. Moore?
No?
And there's the answers you should get.
Yeah, you crank all those unit conversions out, and we get that.
Should we try another one?
Well, yeah.
Silly question. Okay. Now here's the same basic question. We're going to electrolyze magnesium fluoride, but you notice instead of giving us amps and time, they gave us this 50 Faradays. 50 Faradays of current. What does that mean? I know what Faraday's constant is, but they're talking about this in a little different way. Well, just realize that if you see Faradays, 1 Faraday is equivalent to 1 mole of electrons. So really, they've done you a huge favor here. They've given you all of this information, and they've simply told you straight up how many moles of electrons were pumped through the cell. So I can get rid of all of this. And replace it. And say that 1 Faraday is 1 mole of electrons. And if they pumped 50 Faradays of current through, they must have pumped 50 moles of electrons through the cell.
Yep.
So now I would just have to figure out, okay, for magnesium fluoride, what are my half reactions? Okay, and again, the metal is always going to be reduced here. Well, magnesium being a group 2 metal, it's going to be +2. It'll have to gain 2 electrons to reduce to magnesium metal. And of course, fluoride ions are -1. The nonmetal is always going to be oxidized. Of course, you have to remember that fluorine's another one of those diatomics. Right, we'll end up making some fluorine gas. So it's going to take 2 moles of electrons to accomplish that. Okay? So now, home stretch, I think, Mr. Moore, right?
Yep.
If I know 50 moles of electrons have passed, if I want to know the magnesium, I can say for every 1 mole of magnesium, there's 2 moles of electrons. And I can easily change from moles to grams. And similarly, we do the same thing with the fluorine. Looks like to make 1 mole of F2 gas, it's going to take 2 moles of electrons. Of course, it's also fun if you produce a gas, you can work the ideal gas law into this, because you can ask for a volume of fluorine produced.
It
That's
does sound
something-
like fun.
It does. Mr. Moore would definitely do that. He loves the ideal gas.
You know I do.
Yeah. And so these are the answers we got. About 608 grams of magnesium and about 950 grams of fluorine.
Yeah, 50 Faradays is a huge amount of current that has passed
Yes.
through. And I would just remind you that electrolysis, magnesium fluoride is a very stable ionic compound, so it wouldn't naturally break up into magnesium and fluorine. So that's what electrolysis is for taking something that wouldn't naturally happen and forcing it to happen. So you can get pure magnesium this way, we get pure fluorine this way. We don't find magnesium pure in nature because it's pretty reactive.
Yeah.
So we have to do this this electrolysis method to be able to break
Right.
those things apart.
Yeah, this reduction potential for magnesium is negative, I think 2.38 volts or
Yeah,
something.
it's
Magnesium does
very
not
low.
want to reduce, but it really likes to oxidize. And so, as Mr. Moore said, you'll not find magnesium metal commonly in nature.
Mm-hmm.
It's always going to be in an ion form and in a salt of some sort.
Mm-hmm.
All right, are they ready to try one on their own, Mr. Moore?
Yeah,
I think
try
so.
one. Try one on your own.
Okay, here's your problem. Of course, in AP, right, it's all about trying to confuse you, so here you go. right? We have this unknown metal chloride. It's electrolyzed with 50 amps of current for 30 minutes.
0.5 amps.
Oh, sorry, 0.5 amps. And it is found that 0.64 grams of the metal collects at the cathode. Can you determine the identity of the metal? We'll be back in a minute to see if you can do it.
Yeah, go ahead and turn your device off. See if you can do this problem. Like, turn it off. We're not going to stop the camera, so we're going to depend on you to turn and try it first. And Mr. Hevel will see if he can write out the solution for it.
Okay, I'll race you. Okay, let's see, 30 minutes. Minute. 60 seconds. That's our amps again, Mr. Moore, 0.5
0.5,
amps.
yeah.
Point-
Don't give anything away. They're working on it.
Yep, gotcha. 0.5 coulombs per second.
Mr. Martinez, please call 2847. Jose, 2847.
Okay, you ready for us? Here's the solution. We've gone from the time, found coulombs that were transferred, used Faraday's constant, get moles of electrons. We know that M is a positive 2 ion because the formula was MCl2. So there are 2 moles of electrons in every mole of M. Doing this conversion will get you how many moles of M has reduced. And we knew the mass of M was on there, it's 0.64 grams of it. So we can find the molar mass and determine what M is. And what is M?
Okay, let's see. Drum roll. M is
Barium. All right. There's a short lesson on electrolyzing molten salts, finding how much of the salt, how much of the elements can be produced when that's electrolyzed.